Imagine you have a water tank sitting high on a hill. The water stored in that tank has a certain amount of gravitational potential energy simply because of its height. The higher the water, the more potential energy each drop has. Now think of voltage in an electrical circuit in a very similar way. Voltage is like the difference in height between 2 points in our water tank analogy. Just as water at a higher level has more potential energy and will naturally flow downwards when given a path, electric charges want to move from a region of higher voltage, more electrical potential energy, to a region of lower voltage, less electrical potential energy. Here's the breakdown. Water tank height equals voltage. The taller the water tank, the higher the water pressure at its base. In a circuit, a higher voltage means there's a greater push or electrical pressure on the electrons. Water flow equals electric current. When you open a valve, water flows from the high point to the low point, just like electrons flow through a circuit from high voltage to low voltage. Potential energy per unit equals voltage per charge. In our water analogy, every unit of water at a higher level has more energy. In an electrical circuit, every unit of charge gains or loses energy depending on the voltage difference. So if you imagine a battery, its positive terminal is like the top of the water tank, high voltage, and its negative terminal is like the bottom, low voltage. When a circuit is connected, the voltage difference between these terminals creates a pressure that drives electrons through the circuit, much like water flows downhill due to gravity. This analogy helps us understand that voltage isn't the total energy stored in the circuit, but rather the difference in potential energy per charge between 2 points, just as the potential energy of water depends on the difference in height within the tank.